So here's that graph you were given. And generally, so how does the temperature change from 3 to 15? Generally, we got a negative rate of change, so the temperature is going to go down somewhat. And then it's going to go up. When the rate of change is positive, it's going to head up. And then it's going to go down again when the rate of change is negative. Okay? So looking about what time after 3 will the temperature return to its starting temperature. So temperature's going down, right? So if we thought about making our constant rates and then adding all those negative changes, and then we had constant rates here that were positive constant rates, and adding together those, when would the positive rates kind of balance out with the positive accumulation balance out with the negative accumulation? I said around x equals 7 or 307, something like that. So you're just kind of eyeballing. So I just said somewhere around here. All your accumulation from these negative constant rates would balance out with the accumulation from positive constant rates. Somewhere around 307. Questions so far? All right. So when is the temperature the lowest? Well, the temperature is the lowest right here. I estimated that to be about 3.8, or there'd be like 303 or 304, maybe 304. Okay, when the temperature is the lowest, because it's decreasing this whole time, and then it increases more or less than this amount of decrease. A whole lot more, because for a longer time, and you have higher positive rates than you do negative rates, right? So you have a shorter time of lower negative rates. You're going to get a much bigger positive increase here. So the lowest the temperature would be at x equals 3.8, or about 304. Okay, and then the highest then would be, you get all, like I said, you have all this increase, which is greater than this decrease. So around, I said around 313 or 13.2 for x. Okay. Good so far? Okay, yeah, please.
I like the 315 because I think that is the biggest negative rate.
For when it's the highest?
The lowest.
When's the temperature the lowest?
Yeah.
So
I thought the rate is more negative.
yeah, but you had all this increase. You had to consider that at this time you had all this amount of increase. It's not just the time of the greatest negative rate is not going to be your lowest temperature, because you have to consider the accumulation of all the changes in temperature before that. Does that make sense? Yeah. Okay. So now we get to the. So we want a definition for A sub. This is A sub t, the exact accumulation of changes in temperature, or this is like net accumulation, right? Net accumulation. Starting from 3 until x minutes after 3. So here's what I came up with. A sub t of x is the integral, right? So that's what this is our big conclusion at the end of last class. The integral from 0 to x at this particular rate, our constant rate. I used u du. Okay, so maybe this is a good time to ask, why can't you just put x and dx? Why can't you just put x and dx? Why do we need a new variable here? So, you first.
Because that's moving, that u is moving between 0 and x.
Okay. So we're going to say 2?
Yeah, because otherwise you're just using that one variable.
Consider two different, in the situation of two different values, they're not the same. If they're both variables, they're not going to be the same. You can't use the same variable for both.
So what does x mean in this situation? What does x mean in this situation? Yeah.
In this situation, is x a constant?
No, because it's our independent variable, right? It's definitely not a constant because it's the independent variable of our function. So what is x? Yeah.
X is going to be like the max value that we're going to, but u is going to be everything in between.
Okay, good. So x, good. X is where we're starting from accumulating from 0. X is where we finish accumulating. At that, but x is going to increase. But for any given value of x, that's where the accumulation is going to end. And like a couple of them said, what we need then, if we're going to accumulate from 0 out to some value, then we need another symbol to represent x values changing from 0 to x. Because if we put x in there, so suppose we had x in there. Let's just do an example to see what happens. So if we were to do it this way, if it were to be this, then let's make sense of a sub t of 12, a particular value of accumulation from 0 to 12. If it was written this way with x 0 to x and rt of x dx, then it would be the integral from 0 to 12 of r sub t of 12. Don't say d12. Okay. All right, dx. Okay. Now what would that be? So that would be accumulating the changes in temperature from 0 to 12 at what rate? Not 0. What kind of rate is that? That's a constant rate. That's this rate right here, whatever that value is. So if we accumulate starting from 0 to 12 this way, what's it going to do? It's just going to accumulate changes at this constant rate of r sub t of 12. See that? That's what will happen if you do r sub t of x dx. But if we have another variable, it's still standing for an x value, but every x value starting from 0 to x. That will work because then that will get this rate profile that we want, right? Starting from 0, we want to get all the different rates starting from 0 and ending at 12. So we need a different symbol. If we use the same symbol, we just get the constant rate equal to the rate at the end. So that's why we need a different. So commonly you'll see T, but since we had capital T, I just chose U, okay? Questions on the exact net accumulation function? Yes, please?
Would we be wrong if we use the sigma r sub t x sub I times x sub I?
Yeah, because we want to express, if you did that and then you said for really super small delta x's, then that's okay. But the whole point is this is a much more cleaner expression, right? So when delta x gets super small, we've got this much nicer expression to represent exact accumulation. So now when we want to write an exact net accumulation function, we want to use integral.
I did specify with the delta x.
Okay, so it's correct, but it's just not the desired form, right? Okay. So then what's the definition of capital T? If this is what? This is the net accumulation of changes in temperature, and we want T, the actual temperature. We're going to add 40, right? So we're going to have the same function that we're going to add 40 to, because now we're going to start at 40. This is 40 you can think about as all the accumulations of changes in temperature up to 0. All the changes before got us to 40. And now starting from 0, we're going to add our changes according to the integral. And that will give us the temperature. All right, and you were to sketch that, and just make a sketch of that, right? So your sketch started at 40, and then we said goes down for the first, about 4 minutes. So the lowest was going to be around 4, and then up until, I don't know, what was it, 13 or something? I think that's right here. So then from there it's going to head up to about 13, and then head down again pretty fast, something like that. So is that the function T or capital A sub T?
T.
That's T. What would the function capital A sub T look like? Shifted down so that the starting point would be at y equals 0. Or you're right, because for the net accumulation function, you always will be 0 at your starting point, right? So at time equals 0, the net accumulation is 0. To get the actual temperature, then we got to move it up to our starting value of 40. Okay, very good. All right, so then if we want to express the temperature in two ways, we can say T of 10. So the temperature in the fridge, T is our temperature function, so T of 10 is the temperature in the fridge. And then using the integral notation is then basically just using the rule of this function, right? Plugging 10 into our function, so 40 plus 0 to, integral 0 to 10. Okay, and then now change. What about the change in temperature from 301 to 305? So using function notation to write a change, you can do the final value of the quantity minus the initial value of the quantity, or T5 minus T1. No pencils, please. No pencils or pens, please. Just listen. So the final value of the quantity minus the initial. And then we could also express that as the integral from 1 to 5 r sub t u du. Guys, pencils and pens out of your hands, or I'm going to just take your paper and you won't get any credit. Okay? That was the ground rules, right? Okay, maybe Cerny, can you kind of stand up and kind of look? It's very tempting, I know, and painful to not do it. But I asked you, okay? So, you know, we're adults now, so just go ahead and please respect that. Yeah.
Would it be appropriate to put like a sub t of 5 minus a sub t of 1 because since you're just finding the difference?
Okay, great question. Would this give the same value? A sub t of 5 minus a sub t of 1. Would that give the same, would that give the change in temperature from 301 to 305? Yes or no?
Yeah.
Sure, yeah, that works too. Yep, that works too. Because this is, if we're really just focusing on changes, then what doesn't matter anymore? Notice this is not plus 40. Why is it not plus 40? This is, we've seen this in the past. The students really want to add the 40 to this. To this. Does the change in temperature from 301 to 305 have anything to do with the initial temperature? It doesn't, right? It's just, so we could think about, all right, let's start accumulating changes from 1. And then we would want to end at 5, and that would give us the change in temperature from 1 to 5. So yes, and if you wrote out the function, this would have the 40 added, right? It would be 40 plus the integral. And this would have the 40 plus the integral. So what happens when you subtract? They go away, right? They go away, and you're just left with an integral, okay? Largest increase in temperature, same idea. So I'm using the estimates I had for x, 3.8 and 13.2. So t of 13.2 minus t of 3.8. And I have this backwards. Just final and initial, right? I got them backwards. Is that why you raised your hand? Yeah, these should be flipped. 3.8 on the bottom, 13.2 on the top. Okay, any questions on the homework, setting up these expressions? Okay, now we can collect. Yep, bold. Do we have the heading down? Do it one more time. Turn the open side to the right, please, before you put your heading on and pass it in. Open side to the right. So it looks like this in your hand. And what was the heading? Name, 271. Today's date, 25th, 8/25, and your recitation day, M or W.
Is that a live word?
Okay, so let's review this first week. So we talked about we have somewhat arrived at this journey or this endeavor that we arrived at our destination anyway. So what this whole first week was about this. You know how fast the quantity is changing every moment, and you want to know how much of it you have at every moment. So let's review the whole thing. Let's review the whole thing because it sets the stage for the semester. Okay. Principle number 1. So principle 0, we said variables vary. Got to have an image of variables varying, not just meaning a constant, fixed, unknown, but that variables actually vary. Okay, so principle 1, constant rate of change. So here's a real simple example. What does 60 miles per hour mean? What does 60 miles per hour mean? It means you go 60 miles every hour, right? Well, it does, but is that a narrow or broad definition? It's narrow, right? So we want to remember that for any change in time, you can get the change in distance by doing what? Multiplying by 60, right? So in a half an hour, multiply by 60, you get a change in distance of 30 miles. In 5 hours, multiply by 60, you get a change in distance of 300 miles. Okay? So this dy equals mdx, it does a lot for us. The first thing that it does is it gives us a way of understanding this number of a constant rate of change, 60. Okay, principle 2 was the net accumulation function. Net accumulation function. Give the amount of change in a quantity for any value of x when the rate of change was known. That was principle number 2, the idea of a net accumulation function. So at every moment x, it's the amount of change, or the net accumulation, since you started. Okay, then principle 3 was changing rate of change, that realistic rates are often changing rates. Here's that graph of remember the height of the flag. This is the rate of change of the height of the flag. The soldier is pulling hand over hand, right? Pulling the rope down hand over hand. So somewhat would model that rate of change. Constant as he's pulling, but then in between, there's like a pause. And so the rate of change kind of spikes up to 0 in between every hand, right? Okay, so then principle 4 was, and so we said, if you have a changing rate function, this goal of figuring out accumulation becomes much more difficult. Suddenly, it's not, if you have constant rate, well, a net accumulation function is easy. But with changing rate, how do we come up with a net accumulation function? That brings us to principle 4. What did we make? Oh no, not quite yet. So how did we overcome this problem of we've got a changing rate of change function and we want to get amounts of accumulation? The step function, right? The pretend rate function. So that's principle 4. So we're going to mimic the rate function, try to simulate or reproduce the rate function, but with constant rates. And then with the constant rates, we can apply principle 1, right? We can get little changes in our quantity for each interval with a constant rate, and then we could add them up. And we came up with, from that, we came up with an approximate net accumulation function that looks something like this. And you did this, right? So your homework was like the insect population. I said, find the approximate net accumulation at a certain value. And what'd you do? You found the accumulation in the first interval. And then you found the accumulation in the second interval. And then you find the accumulation. Each time you found the accumulation, how? By doing the constant rate times the change. And then the next interval, the constant rate times the change. And then the next interval. And you added all those up. And then you might have had a little bit more in the current value, in the current interval, and then ended up being like a shorter interval, and you added on a little bit more change for that current interval. So this was the idea behind getting an approximate net accumulation function. So now, just want to say, this is just this right here is not the function a of x. It's just kind of the idea of it. It's the spirit of it, okay? How many of you had my calculus or Jennifer Bonney's calculus? How many of you? Oh, it looks like more than half. Okay, so do you remember about the last semester, if it was October, do you remember the actual function that we built? It took us weeks to actually build this function. And it had all the nuts and bolts, so that it was truly a function of x. Okay, So this is just so we can get through this in a week. This is what it was in spirit. Okay, this is what it was in spirit. Okay, so principle 5. We've got an approximation, but we want the exact function, so make more smaller intervals. Better pretend rate function means better estimates of net accumulation. So smaller intervals means a better pretend rate function, better estimates of net accumulation, better pizza. Papa John's. Okay. So here's a version of the flag with small, this is the constant rate function with small intervals, right? Here's the constant rate function with small intervals. Okay, principle 6. What are we going to do after that? So we make the interval smaller to get a better rate function and then a better accumulation function. So then what do we do next? Just make them super small, right? Super small. So small that there's no distinction between approximate and exact net accumulation. So what was our approximate net accumulation? That was the one I just showed you, right? And so we let what? So now we're super small intervals would be like saying let delta x get just really close to 0. Close enough, right? How close to 0? Close enough so that we can't tell the difference in the end, right? And so what happens? Our approximate accumulation function becomes exact. And then our sum of bits of accumulation through the intervals becomes this expression we said last time, right? The integral from a to x, r sub f of t dt. And now that delta x is so small, there's really no difference between completed intervals and current interval in terms of size, right? They're all the same because they're so small. So this just kind of goes away, right? Just goes away. So every time I do that, watch, it goes a different way. Watch. Okay, sorry, go ahead. What does the F stand for? So the F stands for the total amount or total accumulation function that we're after, the exact total accumulation. So and we'll see it. Yeah, see it later. So the and how would we get that? Well, we'd add all the accumulation up to A, and when we do that, then we get the function F. You'll see it. It's coming up here. You'll see it. So that's our exact net accumulation. All right, principle 7, exact total accumulation. So then how do we get exact total accumulation from exact net accumulation? Well, now all the hard work's done. And if we want the function f, the total accumulation, what do? Add however much accumulation we had before A, right? Before A. So that would be, so add any previously accumulated amount to the net accumulation to get the total accumulation. And we have arrived. How much you have at every moment, right? That's what we wanted. And so what is that? That's just f of a, right? If the total accumulation is f of x, if the total accumulation function is f of x, then that amount accumulated before we start accumulating at a would be f of a. And so we made it, right? We made it. You know how fast a quantity is changing at every moment. We're given this, right? We're given this, how fast a quantity is changing at every moment. How much of it do we have at every moment? How much of it do we have at every moment? This. So we can take our rate function. If we write this expression, with our given rate function, we just wrote how much we have at every moment. You know how fast the quantity is changing at every moment. You know how much of it you have at every moment. Okay, so let's take this a step further. So now so this is kind of, we made it, we arrived, we've recapped the math of this endeavor here, or this problem, or this question. Let's take it a step further. What happened? How did that work? Something didn't work there. Let's see here. There we go. Okay, so there was that thing. All right, so this is our total accumulation or amount function. So what I want to do is I want to subtract f of a from both sides. Subtract f of a from both sides, and then it looks like this. Okay? And so now, which are each of these? So both of these then represent what? So now I've got just the integral, and I've got f of x minus f of a. So say just the integral. What does it mean? What is just the integral? What does that mean? What was it? The exact net accumulation function, right? And so then this would be another way of expressing the exact net accumulation function, right? Because they're equal, right? They're equal. So now both sides express the exact net accumulation, which we could also call it the exact amount of change, right? Since A. The exact amount of change since A, but in different ways. That first one is expressing exact net accumulation as final minus initial, right? The final amount minus the initial amount would give you the amount of accumulation, right? Final minus initial. And then the first, this way, is expressing it as the accumulation of many small bits of change, right? So again, what does the integral sign mean? Sum. What are we summing up? Really small changes, right? Really small changes. Rate times change in x, right? Rate times change in x. So we're summing up all the little bitty changes to get the whole change, right? The whole change. So two different ways of expressing the same thing. So now if I flip the order there, I'm just going to flip the order. Does that look familiar? Does that look familiar? So I took my total amount function, I subtracted a, and then I put the integral on the left. What is that? Okay, this is our equation that represents, yeah, you should recognize this is the fundamental theorem of calculus, right? This is our equation that represents the fundamental theorem of calculus. So what is it saying? It's saying that we're expressing the net accumulation function, or the amount of change function, in two ways. On the left, it expresses it as accumulation of bits of change. On the right, it's expressing it as final amount minus initial amount. Okay, so we kind of, really in this first week, there was another goal here that was kind of, and that goal was not only what we've talked about, but also just what is an integral, right? What is an integral? When you look at this thing, what is your mental image of that? What is it? Right. Is it area under the curve? No, it's exact net accumulation. It's exact net accumulation, okay? That's why we spent 3 days on it. Okay. It's not area under the curve. But in fact, next week, that's what we're going to do. We're going to talk about integrals as area. But in order to understand integrals as area, you got to understand that integrals are not area. Okay? In order to understand that integrals as area, you have to understand that integrals are not area. They're exact net accumulation of anything that you want. Height, weight, volume, temperature, area, volume, okay? Area is just one way to apply integrals. So we're going to look at the accumulation of area, okay? But that's just one example, okay? All right. So let's, again, so whenever we see an integral, this is our last chance. Whenever we see an integral in this whole course, we need to think of it as this thing. The sum of bits of accumulation from completed intervals plus a little more accumulation from the partial interval. Okay? But one qualification on this, one condition. What? With a small enough delta x so that the values of this function are indistinguishable from the exact. And when that's true, what about our partial interval accumulation? Okay, watch. Ready? Okay. That's only when delta x is small enough. When delta x is small enough, then that just goes away because there's really no difference between the intervals are so small. They're just summing up all the bits from all the intervals. So let's analyze this. How are they the same, right? How are they the same? So you're going to have a little discussion amongst yourselves. So in each of these two expressions, you're going to show how, for each of these 1 through 4, 1, 2, 3, and 4, how does that item show up in both expressions? So you're going to go to item number 1. How does item number 1 show up in both expressions? Where or how? What part of it? Item number 2, how does it show up in both expressions? Where or how? Etc. So go through those 4, get a partner or a group of 3. Talk through each one of those, and you're saying, because this a function, the second one, it's where integral comes from. It's where the integral function comes from. So when we look at integrals all semester long, we have to have that mindset about it, that image of it, that it's sum of the bits of accumulation at constant rates, right? Okay, so you're doing, and then after 4 comes 7, of course. So you're going to do 1 through 4 and then talk through number 7 and 8, okay? All right, so take about 5 minutes to do this. Get a partner. Go. We know how fast some quantity is changing at every moment. We know how fast the quantity is changing at every moment. Where do we see that in the first one? We said R sub f. Agree with that? That's the exact rate of change. And then in the second one? R of x, right? R of x, which is our, what? That's like our pretend function, right? The constant made of constant rates. So there's number 1. You know how fast the quantity is changing at every moment. We want to know how much we have. How much we have. What's that? A sub f and a. So kind of, yeah, so yeah, that's, but we really need to, is that really how much we have? What's how much we have? So this, if we're actually pointing at the a's here, a sub f and a, then it's, we want to know how much, what? What are those? A and a sub f. How much change, right? How much change we have. So if we're talking about a sub f and a, we're talking really about how much change we have. What is how much in all the and everything that's up there? What is how much we have? Right. And so what? How is that represented in one or both of those? How much we have? What's that? Nope. The integral is the amount of change. Integral is the amount of change. What is how much we have? F. F. The f function. The f function would be then how much we have. Adding the previous amount, right? Adding the initial amount. That would be f. So, but if it's the a function, it's how much change, okay? Which is found by summing up. Where do we see that in the first one? Summing up. Integral symbol, German S, summing up, and then in the second one, sigma Greek s. So we found by summing up the integral symbol or the, okay, and then maybe this is, so this next one is super important, that when you look at an integral, you see where the bit of change is. Where's the bit of change? Someone in the back, someone new. When you look at that integral, where do you see one accumulated bit of change? Yes, sir? Delta x. Is this our accumulated bit of change here? So what about in the integral, though? In the integral. dt, that's our bit of change. Yeah. So he wants r sub f of t times dt. So is it dt, or is it the product of those two that give us a little bit of change in our quantity? The product, right? dy equals mdx, mdx. We get a little bit of change by taking the rate times the change in x, and there it is right there, the rate times the change in x. So that's really important that when you look at an integral, you see that whole expression, the rate times dt, as mdx, right? That's our rate times our change in x. So that's our bit of change. So what's the independent, okay, questions on that? Okay, what is the independent variable of both of these? What's the independent variable? X, right? X. And what does X stand for again? What's that? Yeah, where we're accumulating to, right? Where we're accumulating to. We're starting at whatever, in this case, lowercase a, and we're going to accumulate to X. But then that final amount, that final point of accumulation is increasing, right? So it's a function. It's a function. It's a function of where we stop accumulating. So it's like we keep accumulating to that point, and then it just increases, right? So X is where we stop, but I'm going to put stop in quotes because it's a function. So that doesn't. So we think of X increasing. We think of X increasing, but it's like the left hand, the right hand side, right? The right hand side of the increasingly accumulating amount, right? What is the dependent variable? What's the dependent variable of our integral function? A sub f of x. And one more time, what does it mean? Right, the exact net accumulation of our function, exact net accumulation starting from a to x, right? Exact net accumulation. Or that's the same as the amount of change starting from a to x, the amount of change. Yeah.
Oh, would t now be one of the independent variables?
So t is just another symbol to represent x, right? All the x values between a and x. So it's not the independent variable of the function is x. Yeah, the independent variable is here as x. T then is a new symbol to represent all x values from a to x, increasing from a to x. Okay. Okay, so let's practice looking at some integral symbols here. So I want you to interpret that. Interpret that with all details. So now when you look at an expression like this, what does that mean? What does that mean? So we're going to be setting up lots and lots of integral functions like this. So if you saw that, how would you interpret that? How would you interpret that? Tell the person next to you. Go. What is it? What is this? Okay, Nick. Nick, what did you guys talk about? So tell me what you talked about when you.
We talked about the summation of t starting at 3 going to x with along the curve from the square root of x.
Okay, so starting from 3, so we're starting from 3 up to x, and what are we doing starting from 3 up to x?
Adding all the little changes.
Okay, we're gonna accumulate changes, right? We're gonna accumulate changes starting from 3 to x, and then with one more important detail. Somebody else. What's along the curve? What is the square root of t here? What is the square root of t? Our rate that's our rate, right? That's the rate at which we're going to accumulate those changes. Okay, so when you look at that, you should think this. It's an accumulation function, right? It's a net accumulation function. Even though that's not written, this is the way you want to think about it, as a net accumulation function. And then here would be a perfect way to phrase it. And I'm not asking you to be perfect, because that would just be memorizing this. I want you to say it in your own words, but here would be a perfect way to phrase it. This is the exact accumulation of changes in, say, f, some quantity, we don't know, okay, due to its changing rate of delta x at every moment t from 3 to x. So if you can get something close to that in your own words, I'd be thrilled. Okay, but I don't want you to memorize these exact. I want you to come up with your own way of saying it so that you're thinking through the meanings of everything. Okay, but the exact accumulation of changes in some quantity, say f, due to the changing rate delta or square root of x at every moment t from 3 to x. Okay. Do it again. Go. Tell the person next to you. In your own words. In your own words.
Due to its rate,
Okay, for time's sake, I really want to talk about this one. So how do we want to think about this one? How is this different? Yeah, what's different about this?
this one isn't a function, it's just a value.
Okay. So this represents, he's saying it's not a function, it's just a value. Even though there's a w in there, does that represent just a single number? Okay. But we still want to think of it in terms of accumulation functions. How can we still think of this or frame this in terms of accumulation function? Yeah.
So we could say that it's like the exact accumulation, like this function.
Right.
From 0 to 12.
Right. So 12 then is taking on what?
That's like the maximum.
Yeah. So 12 is what? It's like our input value of a function, right? So it's like we have this function, we're integrating from 0 to any value x at this rate, w squared minus 7. And then we looked at the particular value of a of 12. See that? So it's the same thing. We still want to see that as a function, but we're looking at a particular value of the dependent variable when the independent is 12. So you can say it the same way. It's the exact accumulation of changes through the changing rate of w squared minus 7 at every moment w from 0 to 12. So you get a chance to finish that. So changing rate of x squared minus 7 every moment w from 0 to 12. Okay, I'll get homework up on Blackboard in the next couple hours. Okay? See you Monday.